Okay, so before I get into the technical bits of the talk, I'll just tell you a little bit about what we have going on at RIT, especially as this has changed over the last few years quite a bit. So I direct this Center for Cybersecurity, and this is a research center where we of course have outreach and education mission as well. Briefly, just some of the things that we work on. Jay Yang is an expert in attack prediction. Of course, you know about attack detection. So this is actually trying to guess ahead about what the attacker might be up to. And he has a project with Katie McConkey on trying to do data mining on the dark web and social media and so on to try to figure out whether they can guess a little bit better if an attack is coming on a particular company. We have folks like Andy Manili and Mehdi Miracoli who are software engineers, and they use data mining on code bases, so code mining, and they're looking at things like understanding architectural weaknesses in software and trying to understand how is it that software vulnerabilities come to be in the first place, and can we develop metrics that are useful to improve software security based on this information. We have some folks doing crypto and trusted hardware, not nearly as much crypto as you guys have here, but we have people like Peiza Hu doing machine learning on encrypted data using homomorphic encryption. Ziming Zhao, who's working on the Intel SGX processor and cache-based attacks and defenses there. And Marcin Lukowiak, who works on things, very COSIC looking things like power analysis attacks. And then we have some folks who are in network security of various flavors, such as TJ Chung, who has recently joined us. He was previously with Alan Mislov's group at Northeastern, doing a lot of security measurement type of things. And so he's done DNSSEC deployment measurements, OCSP, and certificate authority type stuff. And now he's looking into Internet of Things. And Ziming, who I mentioned on the previous slide, does lots of different things in security. He basically, I could put him on every slide. He does all sorts of stuff. Is doing software-defined networks as a tool for making better and more efficient security products. And then Hanif Rabari, who does wireless security like full-frame encryption. And one of the things that's exciting for us is that we are, in 1 year, going to launch the Global Cybersecurity Institute at RIT, which is going to incorporate, we have a bachelor's program and master's program in computing security, so specific disciplines, but also the broader Center for Cybersecurity and the interdisciplinary research mission of that, all in a new wing of the Golisano building. And we're very interested in global partnerships. It is the Global Cybersecurity Institute, so we decided, well, we should probably do something that actually is a little bit global in that respect. If you are interested in coming to meet with us, Rochester is a very nice town. Mark Juarez could tell you more about it, especially in the summer when there's less snow. Although if you like the skiing or snowboarding, that is also available. We have a wine region as well, which is lovely this time of year. All right, so the title of the talk is Deep Fingerprinting, blah, 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 but I think we could call it How Attackers Can Read Your Encrypted Traffic and How Could We Potentially Stop It. So, encrypted traffic. Here we have Shelly. Shelly has an embarrassing problem. See, she has athlete's shell. And as many of us do when we have some kind of health problem, we go online to read up more information about it. So she goes to turtlehealth.com. And of course, these days we're all going to be using an encrypted connection for this because we want to protect our privacy about, well, what kinds of diseases might we be having? And that's a good thing because her snoopy neighbor Sheldon is sniffing on her wireless traffic and it's encrypted, so he can't read it. Unfortunately for Shelly, there are more powerful turtle attackers out there. And so what Shredder is going to do is this attack called website fingerprinting. And this is a two-step attack. In the first step of the attack, it's a preparatory step. So Shredder is going to make his own connections to turtlehealth.com. And let's say we have the athlete shell page and we have like curled tail disease or something like that. And for each of these, he's going to send a HTTP GET request, and he's going to get some HTML, and then he's going to make some additional requests, and some additional files start coming back, and so on. And you get this pattern of traffic. When he goes to the tail page, he gets a different pattern of traffic. From these two patterns, he can encapsulate what those patterns are showing, and then store his encapsulations into a database. So that's step one of the attack. Step two of the attack is actually performing the attack. So now Shelly, again, is going to turtlehealth.com. Shredder sniffs the traffic just like Sheldon did, but now he has that database ready to go. And indeed, he sees a match for P1, which lets him know that Shelly is probably going to turtlehealth.com/shell. And this attack has been shown to be pretty accurate. At a level that I think we could say, oh, I would not want the attacker to be able to do that to me if I was using HTTPS to access websites. To give you even more sort of evidence that this attack is a significant threat, we can consider all the different possible threat models that could be using this attack. So like I said, the attacker could be sniffing Shelly's wireless internet traffic. He could have also compromised the DSL modem, the cable modem, or the wireless router, which are often very insecure, having not often been updated and having weak default passwords. It could be that the attacker is Shelly's ISP or workplace who's trying to spy on her to see what she's up to. It could be any of the networks that sit in between the ISP and the website, including somebody sniffing more close to the website, say the ISP of the website. So these are all potential attackers who could use website fingerprinting as their attack. So because of this, I think it'd be good to have a defense. The defense I'd recommend is Tor. Probably all know a bit about Tor, where the client is using 3 nodes, the guard, middle, and exit, to pass their traffic from the client to the web server to provide secure and private web browsing. In Tor, there is still the possibility of the attacker being able to do the website fingerprinting attack. In this case, the attack model is a little bit different than the one I just talked about. Instead of all of those hops between the client and the website, it's going to be all of those hops, but only between the client to the guard and potentially the guard node itself. So all of those are attackers who could see who the client is, could see your IP address and location, and could observe the traffic and try to infer what's going on Shelly's connection. The attack works very similarly. We have the two-step process. The attacker in this case is using Tor to make these connections, observe the traffic going back and forth, extract traffic patterns for each of the websites, use those to train a machine learning classifier, and then that's going to be, instead of a database, using the classifier to go into the second step of the attack. In the second step of the attack, observing the user's actual traffic, extracting the pattern, using the classifier to identify which website it is that the user is going to. And indeed, this attack still works, again with 90+% accuracy, although it is important to note that this is for sites and not pages. So previously we're talking about a single site and we're identifying which pages on that site are you going to. And in this case, we're looking at a different case, which is, well, what if you have 100 sites and you're trying to distinguish between those 100 sites? And so that certainly would make, if you didn't have all the things that Tor is also doing, such as making all of the amounts of data fit into 512 byte chunks that are all the same. If you didn't have that, it would certainly make the attack easier to do it on sites and pages, because sites are going to vary quite a bit from site to site, whereas individual web pages within a single site may share a lot of elements and may be harder to distinguish. But nevertheless, you can certainly imagine there's websites you might go to, individual, like it's one thing to say you're going to WebMD, it's another thing to say you're going to a page particularly about lung cancer or AIDS, right? Or that you're going to a particular religious site. That those types of pages start to reveal more about you. So you can certainly imagine that you wouldn't want it to be the case that the attacker knows these things, and in fact the entire, like a large part of the purpose of Tor is to protect that information about what websites are you going to. Now I mentioned that there's 100 pages that you could be going to, which if you think about it is a bit unrealistic. So that gets us into this notion of monitored versus unmonitored sites. And so the monitored sites are the sites the attacker might be interested in. So the attacker wants to know if you're going to humanrights.com or Facebook or whatever. But there's lots of sites that he doesn't particularly care about whether you're going to. And so there's two versions of this attack that we are interested to look at. The first of these is the closed world scenario. And this, when I present the results today, I'm only really going to be talking about the closed world scenario. And this is in which you assume that the user is going to one of 100 sites, or in our case, we have a data set with 95 sites. So we have one of 95 sites that the user could be going to, and it's very limited. Now, obviously, that's very unrealistic, but what it allows us to do is compare attack A versus attack B, defense A versus defense B. Right? It allows us to do these straightforward comparisons, but again, it's pretty unrealistic. In the open world scenario, the user could be going to any website on the internet, okay, potentially billions and billions of sites, and the attacker's real job is to recognize the monitored versus the unmonitored sites. And if they can do that, if they can say, well, this is one of my monitored sites, then they could use the closed world attack on that data, the same data, and then say, oh, and in particular, it is site 17 that I'm interested in. Now, I have a rule of thumb. Since I'm not going to be presenting the open world results, it gets a little bit complicated, but my rule of thumb is that if in the closed world you get 90+% accuracy, then the attack is pretty dangerous, and you definitely would be in a situation where you wouldn't want the attacker to be able to do that type of attack on you, because the metrics that we're using, precision and recall, they're going to get good precision, and they're going to get reasonable recall if they tune for precision. All right, so Tor, we thought it might help us here. Turns out that it doesn't help us so much. Can we do an improved defense? So there have been some defenses proposed in the literature. Some of them are really heavyweight. They require lots of overhead in terms of traffic bandwidth, or they take 2 or 3 times as long to load the website. And we think that's probably not acceptable to Tor. Tor certainly thinks that that's not acceptable to Tor. So there's a couple of lightweight defenses that we're going to talk about today. One of those is Walkie-Talkie. The Walkie-Talkie was proposed at Usenix 17 by Wang and Goldberg. In this defense, you have 2 sites, site A and site B. And what you're going to do is mold them together such that whenever the user goes to either site A or site B, it looks exactly the same. And the way you do that is you see that we have these sort of bursts of traffic. So we have an outgoing burst, an incoming burst, and another outgoing burst. And what we can do is for the first burst, the first outgoing burst, we can line the 2 sites up and we say, the maximum number of packets for these 2 sites is 3 packets. And so we'll send 3 packets. And so if it's site A or site B, it could be either one. And then we do the same thing with the second burst where you see site B has more packets and so on. In theory, the maximum accuracy that you could ever get with this is 50%. And indeed, they're able, because they can also get confusion between these sites that have padded traffic and other sites that have padded traffic, they can actually do better than that, reducing the accuracy of these attacks to below 30%. In addition, they have what might be considered to be reasonable bandwidth and delay overheads of 31% and 34% respectively. Are any of you network people? Network researchers? No? Okay. Well, then I'll just skip this slide. I'll come back to it if you have that question. The other defense that we might be interested in is WTF-PAD. With WTF-PAD, which is something that Mark worked on with me and some other folks, is if we have real traffic, what it might look like is something on the top, where we have some real packets that come, but it's a very bursty sort of web traffic behavior. So we have a burst of real packets, and then a gap of a delay, and then another burst of real packets. And what we might do is just probabilistically say, I'm looking at the gap between the burst that just ended, and I'm waiting. Okay, I'm going to stop waiting. I'm going to fill in this gap with a dummy burst, basically a burst filled with dummy packets that's going to sit between these two real bursts. And because it's all probabilistic, it's difficult to say that the trace is going to be the same for each time that the site is loaded. And this turned out to work pretty well. It has a higher bandwidth overhead, but doesn't have any added delay. So to kind of compare it against Walkie-Talkie, and is considered to be the main candidate to be deployed in Tor. So at this point, we had SSL compromised by website fingerprinting. We tried to use Tor, but that's also compromised by website fingerprinting. But now we have a couple of defenses, and we're feeling pretty good about ourselves. One of them we even proposed ourselves, so hey, now we're feeling like the attacker is right where we want him, right? Okay, well, if that was true, there wouldn't be any talk left, and we would just all go home. However, that's actually where the talk really starts. So this is deep fingerprinting, work with Mark, my recently graduated PhD student Payap, and slightly less recently graduated PhD student Mohsen. And we're going to be using deep learning. So how many of you are deep learning people or AI people? Okay. All right. So when I give this talk, I like to motivate, why are people so excited about deep learning? I'm sure you hear lots about deep learning. You probably don't need lots more, but I do like to give just sort of the one really compelling example, which is ImageNet. And ImageNet is just this giant database with lots and lots of images. And because ImageNet is too easy to say and remember, they have this acronym ILSVRC, which consists of 1,000 images for each of 1,200 different categories. And this is used for image classification problems as a standardized data set that can help you recognize between a table and a glass and a person and a horse and whatever. And you can say, okay, well, I think it should be... Huh?
Who made it?
I have no idea. Yep. Yeah, and it's been around for a long time. So it's been a very standardized set for a long time. And you might think, okay, well, distinguishing between a glass and a table, whatever, should be pretty easy. In addition to those larger categories, there are some breeds of dog. Here are Canadian Eskimos, Malamutes, Siberian Huskies. I hope you've remembered all that. There will be a quiz later. There are 120 different breeds of dogs that are in the data set to try to help establish fine-grained classification ability of these image classifiers. So, given this data set, why the hype about deep learning? So what we see here is that in 2011, before effective, useful deep learning came to be prominent, we had the state-of-the-art classifier that wasn't using deep learning in 2011, and it had 26% error on what's known as the top 5 classification problem. That means you give the classifier 5 guesses, and if it gets any of those right, then it's correct, and otherwise it's an error. So even though you give it 5 guesses, it's still making it's still not getting the right class 74% of the time. The next year, in 2012, we have AlexNet. So the first sort of effective deep learning classifier in this space. And it drops the error rate by almost 10%. And that really grabs everybody's attention. They start building more and more advanced deep learning classifiers. And you can see that the effectiveness goes up and up and up until in 2014, there was a researcher in the field who said, you know what, I still think I could do better than these classifiers. And he trained himself looking at thousands and thousands of these images and trying to make sure that he could do all the tough ones and so on. And he got himself to have 5% error. And you go, okay, humans are still better than computers, right? Trained human, still better than computers. Well, you know where this story is going. The computers got better than the humans real fast. And of course, they just keep getting better and better. And so you get, on at least fairly narrowly defined, specialized problems, a point where you have superhuman ability on a thing that it wasn't that long ago we didn't think computers would ever really be able to do this quite as well as humans can. And now they're really exceeding what our own capabilities are. So, to make sure everyone's on the same page, I like to, in just one slide, cover what neural networks are, and in one slide, cover what convolutional neural networks are. Very quick. So if it goes too quick, don't worry about it. It's not really, so critical. What we have here is a neuron. So neural networks, of course, are based on the idea that they're modeling what's a little bit, to some degree, what's going on in your brain. And so you have this neuron, and you have on the left some inputs, and on the right the output. And in the middle, you have sort of the activation function, which is basically representing the neuron. And in general, the idea is if you get enough electrical signals going into the neuron, and they all fire at the same time or within a certain amount, then that neuron is going to fire, and that's going to send its signals out to the other neurons. So what does it mean to activate? Well, what it's going to be doing in practice is taking a weighted sum of all of the inputs and then feeding it into a relatively simple function like this. This is the ReLU activation function, a very commonly used one that we're going to use. And all it is if the weighted sum of those inputs is negative, we output 0, and otherwise we output some positive value, which is just y equals x. A very simple function, which is good because we're going to be computing it very often.
So what is the x?
Oh, the x is the weighted sum of the inputs. Oh. So, yeah.
So that would be 1.
So that would be,
1 plus,
yep, w1 times a1 plus w2 times a2, dot, dot, dot. Okay, so that's one neuron. And of course, in a neural network, there's many such neurons, and they form these hidden layers. So you have the inputs going into the hidden layers, which are filled with these neurons that talk to the next layer of hidden neurons, and so on, because it's deep, you'll have more of these layers, and they'll all go to an output. When you start out, you have randomly initialized weights. So you just set them all randomly, and then you feed it an input, and you say, okay, I know what the actual class of this is. This is a glass, and I am going to then feed it the input and see what it outputs. Okay? And we see, is this input right or is it wrong? Well, if we started with randomly initialized weights, is it going to be right or is it going to be wrong? It should be wrong. Okay? And if it's wrong, but in any case, what we're going to do is then use backpropagation to feed that back in and update what those weights should be. So we, through many, many iterations of this, we're going to find weights that do a better job of taking that input layer and making outputs that are accurate classifications of what we want. So, neural networks in one slide. Now, convolutional neural networks in one slide. At this point, you will think I'm definitely cheating on this one slide thing. But I promise you it's one slide in PowerPoint, so you can come check that later if you feel like. So the thing to understand in convolutional neural networks is that what we have going on is a filter. And you can think of a filter like a Polaroid filter that's, it changes to some degree your perspective on what it is that you're seeing. And of course, there's not just Polaroid filters, there's many different types of filters. And each one can accentuate or allow you to focus on different aspects of the image. So some of them maybe highlight the tree or the clouds or the shadow a little bit better. So they all give you a little bit more information. With digital images, we have a very similar concept. That kernel matrix in the middle, that's your filter. And what we're doing is we start in the upper left-hand corner of the image, and we take this convolutional operation, which is just a simple operation that you can see here. You don't need to work it all out. It just gives you an output, which is the first, that 320 in the upper left-hand corner of the output. Then you slide it slide that filter one over to the right, operate on the filter again, you get one more output, and so on, and then down, and then so on, sliding across and down, across and down. And that is what is happening with the filters, and when we talk about filters in a convolutional neural network, and the convolution, that's what's going on. Now that's happening in one convolutional layer. And then if we look at the entire network, what's happening is that on the far left-hand side, we have some filters that are very, very simple. They're looking at very small pieces of the image, and they're separating between different colors, light and dark, just the basics of edges, essentially. As you get further in, the filters start looking at larger and larger chunks of the image, and they start with sort of gathering some filters that show simple shapes, and then we get to filters that can address more complex shapes, and eventually shapes that start showing us things like petals, leaves, the stem, etc., things that could be recognizable to you and me as part of a flower. So, how does that all feed into website fingerprinting? So I'm mostly going to skip through this slide other than to say that there were some website fingerprinting attacks that were very effective, that didn't involve any of this, that didn't involve deep learning in any form or fashion, used handcrafted features, and got pretty good accuracy. And one of the things that is a key feature in these attacks was this notion of bursts. So you have the outgoing traffic and the incoming traffic, and you can say the sequence of uninterrupted outgoing traffic is one burst, and then the first incoming packet starts an incoming burst. And so you can define these as a series of bursts and use bursts to do a lot of the feature engineering that's going on. In our data set, it is useful to know that what we are going to do is represent all the outgoing packets as just a positive one, and all of the incoming packets as a negative one. And all we are going to have in our data is a string for each site, for each instance of each site, of 1, 1, 1, 1, 1, negative 1, etc., as the entire representation of what's happening in that site. And so there was a prior work done here, and well, not just here, but I think primarily here, by Vera Rimmer, who did automatic feature engineering using deep learning, and said that this is a good thing to do because then you don't have a grad student spending a year trying to figure out what are the new good features to use to do website fingerprinting. And that was really nice. They also had a larger data set with many more instances, 2,500 instances per website versus 100 from the prior data sets. So they were able to get state-of-the-art accuracy, or close to state-of-the-art accuracy. They actually found that the Kumul attack performed the best of the different attacks that they tried. So they did use a CNN, like we're going to talk about, and got almost as good as the Kumul attack, which was from prior work. So this work by Rimmer et al. Used an early proposed CNN, which is sort of equivalent to the AlexNet over there on the left, which got about 55% top one accuracy. That is to say, its number one guess as to whether this is a horse or panda or whatever. 55% accurate in 2012. The accuracy has since, however, gone up to, say, the Inception v4net of 2016 to about 80% accuracy on this first guess for the machine learning classifier and what class is this thing. And the improvements are based on the addition of some additional features that we're going to talk about in our design. And so we want to know, are these features actually useful in the website fingerprinting problem, which is, of course, has some differences to the image processing problem. And our other research goal here is to understand if this is going to be effective against defenses. So we talked about, we've got these two lightweight defenses, WTF-PAD and Walkie-Talkie. And this is kind of like saying, well, we have these original images, and we know that those are pretty effective, that CNN is pretty effective on those. But is the CNN model going to be effective when we have distorted images? When we take these images and we manipulate them such that they are a little harder to tell what's what. Although you and I can probably make good guesses at most of these. And so that gets us to our deep fingerprinting architecture. Now the idea is that we're using is to take advantage of these techniques from the work in image processing to see if they are effective in the website fingerprinting problem. So we start with some low-level features on the left, like I talked about, like the difference between light and dark, and we get to things that we can recognize that the high-level features, like wheels you can see in the bottom right-hand corner, that you're going to be able to recognize as parts of cars. In network traffic, can we get the same thing? Now, certainly there are features to be had. This was what Rimmer et al. Were able to show in their work, is that you can extract features from the lower level network traffic and sort of maybe up to sort of medium level depth of your CNN. But what if you have a deeper CNN than that? Can you be extracting even more sort of high level information as well? This, by the way, is a visualization of what's known as the importance score of the network. And so it actually does indicate the yellow line is sort of an average for a site. The green line indicates, all of the green lines indicate instances, individual instances for that particular site. So this is what the two designs look like. The Rimmer et al. Will always be on the right when I talk about this. Our model is going to be on the left. And so let's talk about first this sort of basic block that's used in the models. So in the basic block, you can see that we both have a convolutional layer. That's the filters that we're sliding across the data. Of course, we both have, in both cases, we have one-dimensional data rather than two-dimensional data. So we're sliding only in one dimension. We both use the ReLU activation function that I showed you, but in addition, in our model, in the first two layers, we use the ELU activation function, which is a somewhat different activation function. You don't need to know the details so much, but it is useful to know why we use it. ReLU, as you remember, if you had a negative value, it was 0. But of course, in our data, we have lots of negative values because the traffic comes in, and we have -1 whenever we have an incoming packet. We actually have much more incoming packets than outgoing packets. We have lots of -1s. And we don't want to be throwing away all that data, even after the convolutional processing and so on, like, you know, then performing the activation, you don't want to be losing any of that data, those negative values. So we found that it is more effective to have ELU in the first couple of layers and then to use the ReLU function after that. They use max pooling, we use max pooling. I won't go into what that's all about. But then there's two additional features inside of our basic block. So one is that we use batch normalization, which is BN, and the other is that we use dropout. Now, my understanding of batch normalization is that it is a little bit difficult to say exactly why batch normalization works. There were some initial, like when people put it out, they said, oh, this is why this is going to be good. And then some researchers then proved that that is not what is going on at all. And so I will present sort of what my understanding is of the intuition behind why batch normalization is useful, but I think you should take this with a couple of grains of salt. So to understand batch normalization, it's important to think about gradient descent. You're all probably very familiar with gradient descent, just the hill climbing algorithm. And in deep learning, there's lots of fancy, and in this case, it's valley descending algorithm, I guess you should say. And in deep learning, there's lots of fancy gradient descent algorithms that help you avoid local minimum, all that sort of stuff. But just to refresh your memory, basically at any given point, we start here, we say, here's where I am, here's the error that I have, and I have a slope to that error. And if I was to go left, would the error go down? Or should I go to the right? Right? Which way is going to make my error go down? And of course, this case, I should go to my left, to your right. And so I take that step. And then I take the slope again, and I look at the situation again, and I reevaluate, and I keep moving until I get to the minimum, in which case the tangent is 0, and then we don't go anywhere. And when we're doing this, one of the things that we can consider is a big learning rate versus a small learning rate. So if I'm standing here, if the optimal place for me to be is right there, and I have a large learning rate, I step way over it. I look over there, oh, I'm supposed to be more back over that way. I step way over it again, and I never converge on where I want to be. Of course, if we use a small learning rate, we avoid that problem at the expense of having to take many more steps, so it slows down the learning process. And then, of course, all of this is happening not in like a single dimension of one weight, and not 2 dimensions like I'm showing here, but many, many dimensions. And so what's going on with batch normalization? One way of looking at it is that, okay, so I have this thing where I want to have a good choice of my learning rate so that I don't step way over the thing. But the other thing to keep in mind in gradient descent is I'm looking at the point I'm at now, so I don't know where the actual optimal location to be is. I just know what the slope is where I'm at. And the slope where I'm at might be telling me I should go, instead of going actually towards, really directly towards the optimal place, I should just take a step way to the left. And that might be within the learning rate, but I ended up overshooting where I should go. And then I end up overshooting again, and so on. So it can lead to similar problems to having a big learning rate. With batch normalization, you constrain what you're going to do in any of the dimensions that you go in. And in this case, I'd say, well, I should go straight to the left, but it says that batch normalization says that I should only take a step at most of, say, 30 centimeters in any given direction, so I'm only going to go this far. And that's going to help, I guess in a lot of cases, keep you from ending up in this sort of ping pong type of situation. So then dropout. So what's going on with dropout is, you can think of it this way. If in training, we have these really nice examples of these dogs. Oh, these are all dogs. I can learn what these are. And then when it comes to testing time, you get an example that's a little bit special, shall we say. And you go, oh, I don't know what that is. That didn't look like any of the things I saw before. Yeah, I'm confused. And the problem is that when we have a very deep network, we're especially prone to just memorizing the pictures, right, and overfitting on the training data. So what Dropout does to try to prevent that is something rather non-intuitive, which is each time we go through, we're going to take, say, half of the neurons randomly selected and just cause them to evaluate to 0. So basically like removing half of the neurons. And then we do that for one input, and then we have another input, and then we have different neurons that we've randomly selected to output 0. And what this is doing is, well, we still have this really deep network with lots of filters in it. So there's lots of things, lots of different aspects it could learn. But one of the things that it's not going to be able to learn very well is to do actual memorization. Because if it starts to do actual memorization, well, it's lost half of its ability at any given point to memorize those exact features. Yes?
Do you take that one picture and kill some neurons neurons once, or do you take that one picture multiple times and then kill different neurons?
Well, when we're doing training, so like these are, let's say that even though I showed you earlier, there's actually 120 different breeds of dog and blah, blah, blah. Let's suppose a dog is one class.
Yeah.
Within that class, we might have 800 training samples, and each of those is a different picture, and we're only going to run each one of those pictures once. But for each of those pictures, both within that class, within all the other classes, we are going to do a randomly selected set of the neurons, drop them out for each picture individually.
In training?
In training, yes.
And in testing?
In testing, you still have all the neurons. Yeah.
Okay, so you kill them in training?
Yeah.
And you kill different ones for each training sample?
Yes.
You use once?
Yes. So it turned out this is a good way of, even though you've got a deep network, so it's able to learn lots of things that tell you something about dogness in a generalized way, prevent the classifier from memorizing the individual pictures and heavily overfitting the data. So with these different techniques from the prior literature in image classification, we put them into our model. We did lots of hyperparameter tuning, which is just tuning all the knobs on this thing to see what's going to work the best. And overall, we end up with a network that is approximately 3 times deeper in terms of the number of layers than the prior work. So much closer to sort of the state of, not the full state of the art, but sort of the recent state of the art in image classification. And how does it do? So against Tor, non-defended, so just regular Tor, we cut the error rate, you could say, from the best attack, which is Kumul. So not, again, so this is the one not using any deep learning at all, from 2.7% to 1.7%. So that's not bad. Improvement is improvement. What about defended data? Well, this is the Walkie-Talkie defense. Now, again, this is the one where you've got 2 sites, site A and site B, and you're merging them together to form one pattern. So every time the user goes to that site, they get the same pattern, and so you can't distinguish between site A and site B. The theoretical maximum accuracy then is 50%. We get 49.7%. So pretty good.
But how does the defense work with 95 websites? You always use 2 and then...
Yeah, so you have to take, you have to take the 2 sites. In fact, I think for this we might have had to use their data set because it's a little bit more, did we use their data set? Do you know if we used their data set or?
We actually collected our own data set for this.
Okay.
We had to modify the Tor browser to implement Walkie-Talkie in the Tor browser.
Okay, well, to implement the, that one part of Walkie-Talkie. Yeah. It's not a full implementation of the defense.
That's not the padding part.
Yeah, so the padding is done in simulation after the fact. But yeah, you kind of say, okay, for a closed world, you've got these 95 sites, and you pair this site with that site, and all of the data has that site and those 2 sites paired.
And the pairs are symmetric?
Yes, the pairs have to be symmetric, and they have to be fixed.
What is the classification task? Distinguish between those 2?
No, so then the classification task is, so now you have one of them so now you have an instance from say you have your site A and site B that have been merged together. You have an instance of site A. Now, of course, any instance of site A should look just like any instance of site B. Then, and say, is this an instance of site A? So the best is, so you're guaranteed, like if they have perfect merging between the 2 traffic patterns, and this is the only data you have to go on, then you really can't do any better than 50%.
Yeah, so the classification task is this an instance of site A or B or C or D? But the defense guarantees that there will be always 2 instances that look the same.
Yeah.
But then I think it's weird to get to 20%, for example, because before you had like 3% error rates or something like that. And now you can make 1 out of 2 websites
Oh, so what's happening?
One of two websites wrong.
So are you asking like?
I know that two cases I will be correct, I guess. So my error rate should not go down to 7%.
Oh, but so it could have. So there's 95 possible sites. It could be. Right. It could be any of those 95. If you were guessing randomly, your success rate would be 1 out of 95, not 1 out of 2.
Yeah, but I assume I have an error rate of 3%, so I will probably be correct in like 95% of the cases. I will be doubting in only 1 out of 2 sites. Something like that. No?
No. So you've got the 95 sites. You, if you have a not very good classifier, so this classifier doesn't do very well, then what it's just not able to, it's not able to narrow it down to
Yeah,
the 2
the
sites.
cases have an error rate of 3%, of course. The
So
one that had near perfect error rates of
So
around
this is
3%
not error rate, this is accuracy.
yeah, this is accuracy. So this is
Doesn't matter. It's 1 minus the other, right? So and then you indeed go to 50%. For the one that was near perfect at the beginning, does go to 50% accuracy.
Previous slide?
um,
Yeah.
Okay, they are in 90 something anyway. They are not so far.
oh, okay. But so the other thing is that in addition to making 2 sites look the same to each other, it is just adding a bunch of cover traffic, right? Through this process, it's adding a bunch of cover traffic. And because of that, a classifier can get confused not only between one site and another site and the site it's paired with, but other sites as well that have also had cover traffic added to them. That's what's, yeah, I see what you're saying is,
But the train also protected.
yeah, so yeah. Mhm.
The other thing is that different instances of the same page are
No,
different.
this is sites. You said
Yeah. So different instances of the same page are going to be different.
So you're taking like noisy samples
Yeah,
when you're training, yeah?
Yeah,
Yeah.
but
but
your data set only contains sites, right? It's 95 sites.
yeah.
Not pages within one site. It's always the same page.
Yeah. It's always the same.
Whatever.
But there's variance. I mean, it varies even if you collect it now and then a second later, it can vary. And then if you collect it now and then some of our data, it could be up to 2 weeks or so in some cases, up to 2 weeks or 3 weeks later that you collected, and then things can definitely have changed. So if you're going to CNN.com, the news changes, and even from one instance to the next, even within a second later, not only can the news have changed, the ads that you get and so on, they can also start to change, right?
I'm not sure you collect your database in these circumstances.
Well, I mean, it's
Totally different.
it's sort of a realistic way to capture the data in terms of what can an attacker realistically do as well. So you can't just have, you can't just take a supercomputer and throw it at it and say, go collect everything all at once, and and then it all is beautiful and perfect and very, very similar to each other. I mean, unless you're assuming the attacker also has that capability, and we're just not,
Continuously.
huh?
Continuously.
Yeah, continuously, right? So like that also that the attacker has, because then the user, then they're going to perform the attack. If they perform the attack a week later, of course, all those changes have to be accounted for. So I think actually that would make the classifier less robust in a real attack scenario. You'd want to have it collect the data over a period of time.
I have a question about Walkie-Talkie because you pair the 2 sites
Yeah.
and then you keep that static. So what if the first sample of the 2 sites is super similar, but then it evolves differently? Do they still get paired? Or do you change the pairing? Or that's
It's not dynamic at all.
It's
It's,
not dynamic.
yeah. In the paper, they talk about pairing sensitive sites with non-sensitive sites. So you might pair, humanrights.com with Facebook because one is potentially sensitive and the other is not. And
What if one of them, so you had site A, site B, and the modified one, right?
Yep.
But now in the meantime, site A now has 4 instead of 3.
Then you're in trouble.
And now I'm going to site B and I'm putting 3 because I still assume site A has 3.
Yep.
So that doesn't work. Yeah.
Yes, and we have tested that in the meantime, and
That's a problem.
it all sorts of doesn't work. Is what is our finding.
And question.
Yep.
Does it, I don't remember, but does it also pair sites with similar size?
It does not.
So, okay. It
Right.
might happen that you have a small site group with a very big.
You could,
and
yes.
end up with a lot of overhead.
You do. I think that they, of course, that's their average result, right? Which is fair enough. Like you get an average result, and that gives you a reasonable estimate of the cost of this thing. There might be some instances where a user gets a particularly slow download of a particularly small site because of this, but
Oh, okay, but then they are not trying to minimize like pair things that are similar.
right. Yeah, they're not doing that. Yeah.
Maybe that makes it easier to make a confusion because they are already similar.
It would be less expensive to do it. Yeah. But it wouldn't make it more confusing because if you assume that,
Equally confusing, but much less
yeah,
width and less.
sure, it'd be less overhead. Our experience with Walkie-Talkie, having tried to do the implementation and gotten it functioning but not really working, if you to say getting it working according to spec, but the defense not doing what it's supposed to do because the page changes every time. I don't see how it's going to work as a real defense. And so there's not much, yeah, you could do some things to optimize it, but since I don't think it works, then I don't think it's a good idea to even waste time thinking about it because it doesn't really work. So.
Because of obsolescence.
Just because even if you have really exactly the same stuff on the site, each instance looks different every time. Every time you get it, the instance looks different. The first burst has 37 packets. Now the first burst has 34 packets, and the next burst has 3 more packets because that got added on. Or maybe they didn't get it, they just disappeared this time, or they got more. Like you can't handle any of those.
I guess the problem is that aiming for indistinguishability between two, you have to be like really solid in not having any minor differential. And I guess this
Right.
variance of pages has too much differential.
Yeah. I mean, you could potentially also manage it by greatly increasing the amount of delay so that when you just wait until the burst has completely come. If the entire burst has come and you are confident that the entire burst has come, then you can send it, right? Pass it on. And then you do the same, and you have to do it both direct, and it would add a tremendous amount of delay. We don't see how to fix it, but WTF-PAD. So this one, this is the one where we're adding these dummy packets. Well, I'm sorry to say that that we broke our own defense, and by quite a bit too. So even though, as you might remember, we were adding like 54% bandwidth overhead before, in this study of it, we ended up with 64% bandwidth overhead. Even with that much bandwidth overhead, we are still getting over 90% accuracy and good results in the open world as well. So that didn't work too well. So we were already talking about some walkie-talkie problems. Another walkie-talkie problem is if you say, well, what if you give the attacker 2 guesses? So before we talked about top 5 prediction for images, what about top 2 prediction for websites? And here we get 98.44%. So indeed, you might not know whether it's A or B, but you can pretty much tell it's one of A or B. And all the implementation challenges that I just talked about. So to conclude, before I open it back up for questions, we looked at these 2 questions. If we use a deeper CNN model, Can we get effective website fingerprinting? And the answer is we certainly can. New state-of-the-art results there. And against a deeper CNN model, against some of the defended traffic, which is like these distorted images, can we get effective results there? And we get 90% accuracy on WTF-PAD, 98% accuracy, top 2 accuracy on Walkie-Talkie. So our attacker is happy. That's unfortunately where we have to leave things, where the attacker is excited, although we're trying to work on defenses. Quick shout out to the sponsors, and I'll open it up to more questions.